Uranium is a metallic element that was discovered by a German chemist in 1789. The significance of this discovery wasn't understood for a century and a half. In 1938, scientists figured out that uranium atoms could be split to produce energy. The size of a fireplace log, this nuclear fuel bundle generates a lot more heat. It's packed with enough uranium to power 100 homes for a year. To obtain the uranium, they tunnel 1,640 feet underground at this site in northern Saskatchewan. This mine is the largest source of high-grade uranium in the world. The uranium ore lies beneath a bed of water-saturated sandstone. To reach it, they use drill bits studded with tungsten carbide buttons. Like knuckles on a fist, the button bits punch into the rock face. These first holes are for pipes that will pull heat out of the ground and freeze it around the ore. The miner operates the equipment by remote control. It transfers a new piece of pipe to the end of the drill roughly every 5 feet to penetrate 426 feet into the sandstone bed. It takes up to 8 days to install just one length of pipe, and there are 200 of them. Workers configure the pipes so they surround the ore deposit. These freeze pipes will stabilize the ground, and they'll also turn high-pressure groundwater to ice, so it won't interfere with the actual mining. A freeze plant above ground chills calcium chloride brine to minus 22 degrees Fahrenheit and sends it through the freeze pipes. The brine absorbs heat as it freezes the ground and loops back to be chilled again. Above the uranium deposits, workers now gear up to mine the ore. They'll use this bit to chew into the ore body in order to make an initial small diameter hole known as a pilot hole. The pilot hole maps out the drill route to ore, and it creates an entry point for larger mining equipment. From a raised position, the bit bores vertically into the rock to drill the pilot hole and reach a specific level below the ore body. They're now ready for the reamer bit. The reamer has numerous button-encrusted wheeled tentacles. As this animation shows, the drill pulls the reamer up the pilot hole, widening it, and the broken ore falls into what's known as an extraction chamber. Here, a tram operated by remote control scoops up the rock. This remote control system keeps miners a safe distance away from falling rock hazards. It also minimizes their exposure to the radioactive uranium in the ore. As another precaution, workers continuously ventilate the mine, introducing fresh air every 20 minutes. Steered by the operator's joystick, the tram delivers the ore to a scanner. By measuring the amount of radioactivity in the ore, the scanner determines the uranium content is about 15%. In much of the ore, the uranium content is even greater, on average around 18%, and that's considered to be very high grade. The train now empties the ore into a chute. Cameras follow the rock's journey to the next station. Then, from a control room, an operator manipulates a hydraulic hammer to smash the ore to bits. The broken ore then migrates to a mill that grinds it into a fine sand. They add water, and it becomes slurry, which they then pump to the surface. Trucks then transport the uranium ore slurry to a mill nearly 50 miles away. They pull into a special offloading facility. The support for a vacuum system aligns with the tote that encases the slurry tank. Once in position, a vacuum pipe drops into the tank and suctions up the slurry. Cameras provide a live feed of the unloading progress to a control room almost 23 feet away. After a wash and a radiation check, the truck leaves. Stay tuned for the transformation of uranium into nuclear fuel. Just one fuel bundle of uranium contains the same amount of energy as just over 71,000 gallons of oil. But uranium can't simply be chipped away from the rock it resides in. It must be chemically separated and processed to make it into usable fuel for a nuclear reactor. Acid dissolves the uranium, but not the rest of the rock. It settles to the bottom of these tanks. The uranium acid solution flows forward, leaving the unwanted minerals behind. Using a series of chemical reactions, they further purify the uranium. They then roast it at 1562 degrees Fahrenheit. This concentrates it into a jet black powder. The uranium powder flows into 55-gallon steel drums. A worker taps the lip of the drum to remove residual powder. He then puts the lid on and activates a press that secures it tightly to the drum. As an extra precaution, he seals it with a steel ring. He labels it to indicate the drum's contents, weight, and radioactivity. Workers stack the drums in a warehouse to await shipment to the next processing plant. There, the uranium goes from black to yellow as they convert it to uranium trioxide, an interim chemical form in the processing chain. They ship the uranium trioxide in specially designed inverted cones. Upon arrival at the next facility, a valve opens at the bottom and the powder flows into conveyor tubes that take it into the plant. Inside, workers dissolve the uranium trioxide powder in acid. A worker takes a sample to test the density and the chemistry and confirms that both are acceptable. They then add a chemical to turn the dissolved uranium back into a solid. After more processing, the uranium trioxide becomes uranium dioxide, the chemical form required for nuclear fuel. Spinning the uranium dioxide mixes the different sized particles to make it a more homogeneous blend. The chemical processing has also caused the uranium to change color again. It is now a fine black powder. Using several tons of pressure, tools shape the uranium dioxide into pellets. A revolving wheel with protrusions guides the pellets into a channel conveyor. The conveyor takes the pellets into a furnace. Over 24 hours, the heat removes pores in the pellets. The pellets shrink, increasing the density of the uranium. The particles fuse together and harden into a ceramic. Here is a pellet before and after baking. A robot arm now loads the pellets onto a tray and levels them. A conveyor moves the tray forward. Ahead, another robot places zirconium fuel tubes on a rack. Zirconium is a metal that's highly resistant to both heat and corrosion, but neutrons will pass freely through it during the fission reaction. The rack of tubes meet up with a tray of incoming pellets. A robotic loader pushes the stack of 30 pellets into the tube. Another robot delivers the rods, one at a time, to an automated welder that caps the ends. The next robot retrieves the completed uranium fuel rod and transfers it to an assembly fixture. It arranges a total of 37 rods in an upright position within the fixture. After the rods have been welded and the bundle capped at both ends, a robot transfers it to a scale. This weigh-in confirms that there is the correct amount of uranium in the bundle. Prior to burn-up in a reactor, the amount of radioactivity emitted by nuclear fuel bundles is very low, and they're safe to handle as workers prepare them for shipping. They're now on their way to the power plant, where they'll be sure to generate a reaction.